Okay, so today I'm going to go through cached memory. This is chapter 4 in the 10th edition of the book. If you have the 11th edition of the book, this is going to be divided up into chapter 4 and 5. And so I'm going to do the first half, which is chapter 4 in this presentation. I'm going to do the second half, chapter 5 in the next presentation. So we'll kind of deliver things in a bit of half and half type of way. So memory is actually quite interesting because it seems like a pretty simple concept, but there's actually a wide variety of implementations and wide variety of ways of characterizing memory. And this shows itself in the hierarchy of memory subsystems, which we'll get to in a few moments. Chapters 4 and 5 from that 10th edition deal with internal memory. That's the physical textbook. And chapter 6 deals with external memory. There's, again, slightly different partitioning of things in the 11th edition of the book if you purchase the online version from Pearson. So we'll get into the different memory types, and it's useful to think about, well, how can we characterize memory? And there are different characteristics that memory can exhibit. One is location, is an internal processor registers cache or main memory, or is it external, like an optical disc, a magnetic disc, or even a tape? Back in the day in the 1970s, I used to have to record a lot of my programs on cassette tapes, and then they would get garbled, and I could no longer record load my program, so I'd have to rewrite them. And that's how I kind of got good at programming, was the unreliability of the systems at the time. Capacity is another characterization of memory, the number of words and the number of bytes that it can hold. Unit of transfer, you can characterize those both in terms of words and blocks. Access method, sequential, direct, random, or associative. Performance, the access time, the cycle time, and the transfer rate. And then the physical type, is it semiconductor, magnetic, optical, or magnetical optical? And physical characteristics, is volatile. That means, does it go away when the power gets shut off, or non-volatile, stay there even afterwards? Is it erasable or non-erasable? And how do we organize things? And so in terms of capacity, this is typically expressed in terms of bytes or words. And common word lengths are 8, 16, and 32. So you may have a 32-bit word, which would be 4 bytes. And so you would have a different word capacity than you would a byte capacity. And a unit of transfer is also different based on words or blocks. So the unit of transfer is equal to the number of electrical lines in and out of main memory, and that could be equal to the word length, or it's often larger with 64, 128, or 256 bits. So, and we can clarify that a little bit with word being the natural unit of memory and the organization of it, addressable unit, which is the word, and then the unit of transfer, which can be different from the number of words. So location, capacity, and unit of transfer. Location refers to whether the memory is internal to the computer or external to the computer. We don't have as much external nowadays, although I still see people using jump drives from time to time, but it used to be, like, for example, floppy disk would be something that was external, or a cassette tape, or a optical disc that you had a CD, CD-ROM, DVD. Internal memory is often equated with main memory, and that might be different than your hard disk. So, a lot of times when we say internal memory, we're talking about the main memory versus the hard disk. And the processor has its own local memory in the form of registers, and cache is another form of internal memory, which is going to be the topic later on in this chapter. External memory consists of peripheral storage devices that are accessible to the processor, and those go through the I/O controller, so they can be a little bit slower. Capacity memory is typically expressed in terms of bytes, And unit of transfer, again, we talked about that being equal to number of electrical lines in and out of the main memory module. Those could be different than the individual words. So sequential access, good old cassette tape. There's the awesome mixtape if you'd like to play that. It's from one of the Marvel Comics movies. Not a bad mixtape, I guess. And basically with sequential access, if you ever had a cassette tape, I realize that I may be one of the few that actually have had one. You had it in a specific linear sequence. So when you wanted to go forward a song, instead of just pressing forward, you would have to hold down the fast forward at the same time as the play, listen to the squeal. When the squeal stopped, that was time to cue the next item. And that kind of burned through the cassette tape. So you tended to listen to them sequentially all the way through, flip them over, listen to them all the way through on the other side. And it also had a shared read-write mechanism. So there was a play head and a record head. And I think back in the 70s, you did have some cheaper devices that were play only, but most of them were play and record. And if you were back in the 1970s and you had a home computer, something like a TI-99 4A or a Commodore 64, a lot of times you stored your programs on cassette tapes because they were readily available. And I think it wasn't until 1980 something that I got my first actual disk drive for a home style computer that came when I had a Commodore 64. But the TI-99 4A, all of my programs were on cassette tapes, and they degraded pretty rapidly. Direct access, and this is another piece of old technology pictured here. Again, you have a shared read-write mechanism. Here in the case of the turntable, it's read only. The individual blocks or records have unique addresses. You can think of these as the tracks on the vinyl. And access is accomplished by direct access to reach the general vicinity. That's like picking up the needle and moving it over to the track break. And then sequential searching and counting to reach the final location. Say you want to hear a particular riff in the song. You have to wait for it to spin around to reach that particular riff. So the access time is variable depending on where it's located on that disk. And this is the same way that your hard disk works as well. Each addressable location in memory has a unique physically wired addressing mechanism, and the time to access for random access memory, here you have each one has a unique address, and it's independent of the sequence of prior accesses, and it's constant because you're going directly there. So this is like direct access memory. So you can select any address at random, and it can be accessed in the same amount of time. So main memory works this way, and cache systems, some of them are random access, although a lot of them are associative access. And associative access is random access that enables one to make a comparison of desired bit locations within the word. And it can do this for all words simultaneously. So you retrieve a word based on a portion of its contents rather than its address. And again, the retrieval time is constant. And this one's pretty much exclusive to cache memory. So in terms of performance for memory, we look at two things, the performance and the capacity. And there are three performance parameters. One is the access time, and for random access memory, it's the time it takes to perform a read or write operation. For non-random access memory, it's the time to position the read-write mechanism at the desired location, such as that needle on the turntable. And also another one is memory cycle time, and this one's again kind of a internal memory thing. Basically, it's the access time plus any additional time required before the access can commence, and so that may be for the time required for the signals to die out on the bus line, along with the access time. And then the transfer rate is the rate at which data can be transferred in or out of memory. And for random access memory, it's equal to 1 over cycle time. So different physical types are another characterization of memory. There's a semiconductor memory that you see pictured in the upper right here. magnetic surface memory, which is like the disk, optical memory, which is the CD and DVD ROMs, and then magnetical optical that you see pictured on the bottom, which is kind of a combination of magnetic and optical. Physical characteristics can also be divided into whether it's volatile, does the information decay naturally or gets lost when electrical power is turned off, like in your RAM, or non-volatile, it stays there, like if you record on a CD-ROM. There's no electrical power needed to maintain the information on a CD-ROM or on your hard disk. You can turn off your computer, boot it up, and again, you'll still be able to get to things on your C drive, hopefully, unless you have a really old computer, in which case, wish you the best of luck with that. And then the other thing is whether it's erasable or non-erasable. If it's non-erasable, it can't be altered except by destruction. So I have a little shredder behind me if I want to get rid of CD-ROM. Basically, I can run it through the shredder, but it's a read-only memory, so I can't write over it. Now, you do have CD read-write, which was a little bit of a newer technology, but it wasn't as reliable as the CD-ROM, the burned ones. And this all goes to the memory hierarchy. So again, we can think about memory as how much, how fast, and how expensive. And there's trade-offs. So, faster access time, it's going to cost us more per bit, because that's closer to the register and closer to the processor. Greater capacity, well, that's a smaller cost per bit, but that's going to slow things down a little bit in terms of its access time. So, for example, it doesn't cost very much to have an external hard drive, compared to cache memory. But it does slow things down a little bit. If I want to go get that external hard drive, I have to go over to the drawer, get it, plug it into the computer, and then it gets accessed in kind of the same way as I/O. So that's a little bit slower than if it's on the cache or on the chip itself as a register. So this produces the memory hierarchy. Here's a visualization of it as you go down. So you start at the fastest memory, which is on the CPU itself, which are the registers, and the cache can also be on the chip. Those are really fast, but there's more cost associated with them. As you want to increase the capacity, it will also increase the time it takes to access them. So it takes a little more time to read things in from main memory, and to read in from solid state or offline storage, it takes much more time. The other thing we want to keep in mind is we want decreasing frequency of access. So things at the bottom we're not accessing as much. So think of it as like long-term storage. Everybody probably has a place in their living quarters where you put things that you don't access very frequently, and you can put more things in there. Think of even a storage locker, although I don't advise renting a storage locker. That would be something that you were accessing infrequently. So it would take a longer time to get it than something that you're accessing frequently. Like here, I access a pen frequently to write things down or jot down notes, or take attendance. If I wanted to go get my old coin collection, well, I have that in a storage closet here, and I would have to dig through the storage closet in order to get that old coin collection. So it's less frequently accessed, but there's a heck of a lot more storage space in the storage closet here in the condo than there is, on my table. There's a lot more storage in the closet than in my immediate working area. Another view of it is you can look at this as a graph. And over on the y-axis, you have increasing cost per bit along with increasing transfer rate. So the rate is much higher as you go up the y-axis. As you go over on the x-axis, you have increasing access time, but also increasing size. So, size and cost per bit. So as the size increases, the cost per bit should increase. A related concept for this and why you have the memory hierarchy is something called locality of reference. And so when you're executing a program, the memory references by the processor for both data and instructions tend to cluster. And this can be due to things like data structures, instructions coming one after another. Think about that program counter. We're not, if we're not doing a lot of jumps, the next one will come in the immediate vicinity. And so over long periods of time, the clusters tend to change, but over short periods of time, the processor is primarily working within those fixed clusters. And if you want to see an example of how this works with two levels, you can look on page 126, and they have an example. I may work through that in class that talks about being 10 times as long for having to pull something into the cache, and so you can get kind of a performance value on it. So again, memory references tend to cluster. Programs tend to be sequential, move from one instruction to the next with not as many branching instructions as you might expect. And so in most cases, you can fetch the next instruction immediately after the current one. So you can read a block into the cache, and then you're pulling things from the cache as opposed to main memory. So, and it's rare to have these long uninterrupted sequence of function calls corresponding by a sequence of returns. That might be something you would see in an ACM ICPC programming contest or in the supercomputing cluster programming or supercomputing conference programming contest, something like that designed to stress it out. But in general, we tend not to do that. And iterative structures also help out because they repeat the same commands. When you're doing a for loop, you're repeating the same command. So you have this locality of references where basically things are all close together. The references are going to be close to one another. And last but not least, data structures such as arrays also have closely located memory. Think about an array, the next move is the unit of the type, like for an integer to be 4 bytes, moving forward 4 bytes in memory. So, all very close by. And, this plays out in programs. They've done some studies on different programming languages. So here's Pascal, a scientific application. Assignment statements take up 74%. And, again, the assignment statement is fundamental to imperative programming. Loops, 4%. Call, which is like a function. If statements, 20%, and 2% go-tos. Okay, hey, Pascal, they still have the go-to, and 0 other. Fortran for student programs. Again, assignment statements take up the bulk. Conditionals, 11%. A lot more go-tos with the student Fortran programs, obviously, and other. Wonder what other are. Take up 7%. C system programs are a little bit different. The assignment statements, still 38%, but conditionals are 43%. So you might not get the same amount of locality of reference with these C system programs. But certainly with Pascal and Fortran, you're going to have that locality of reference because you're not having as many branching statements. But that C system program certainly didn't have the same great locality of reference. There are 2 types of locality. Spatial refers to the execution tending to involve memory locations that are clustered. And you can exploit this by having data structures such as arrays that have adjacent memory. Temporal locality refers to the tendency of a processor to access memory locations that have been recently used. And think about a routine or a loop. You're going to keep referencing those recently used instructions, and so you can keep them in the cache for faster access. And you can also exploit this by having more than 2 levels of memory. And you can have different levels of cache. You can have level 1, level 2, level 3 cache, and then move things back and forth between level 3 to level 2 to the level 1 as you want to use them. So after you're done with level 1 cache, if you don't think you're coming back to that portion of the program, you can get rid of that, move the L2 cache up to the L1. L3 goes to L2, and then you bring in the next block that you think you'll need for main memory. And then virtual memory, which gets stored on the disk, and that's probably the slowest one. So in terms of a summary of levels, you have the registers, which are CMOS technology. The unit of transfer is the word, 32 bits, managed by the compiler. The cache is static RAM or embedded dynamic RAM, EDRAM. It's 32 bytes that it has for its unit of transfer. So again, much larger unit of transfer, a little slower. It's managed by the processor hardware. Main memory is the dynamic RAM, and the virtual memory page, which is 1 kilobyte, again, larger unit of transfer, but a little bit slower, and that's managed by the operating system. Secondary memory is your magnetic disk, your hard disk, which is disk sector is 512 bytes, and it's managed by the operating system and the user. And then offline bulk memory is the magnetic tape, and the unit of transfer they don't list here, but that's managed by the OS user. So that's it for part 1. This cache memory principles is going to get us into chapter 5 in the 11th edition, but it remains chapter 4 in the 10th. So thanks so much for watching.